have Pavel Putrov to tell us about the comics of Kapustin-Witten equation.
Yeah, I would like to thank you for inviting me to give a seminar. So my talk will be about some sort of physicist kind of approach of counting the solutions of Kapustin-Witten equations in some sort of indirect way related to kind of some sort of resurgence phenomena in Chern-Simons theory. And the plan of my talk is following. So first I will start with some sort of motivation where I will be kind of quite kind of schematic, and then I will be a bit more systematic. Then I will kind of review about the relation between counting of gradient flows via Stokes coefficients in finite dimensional case, and then kind of how one can kind of transfer this knowledge to Chern-Simons theory, and then consider kind of how one can produce using this kind of correspondence, how can one produce explicit counts for a class of three manifolds known as plumbed. And so this is a mostly is kind of well, this part will be mostly a review and kind of based on the works by Witten, and also kind of more practical kind of approach, which was done in the paper by Gukov, Marini, and myself. And the last part will be a kind of a part of a bigger joint project, of a bigger kind of project joined with Sergei Gukov. Okay, so let me start with some sort of brief motivation. So kind of motivation is to try to kind of introduce some new kind of homological invariants of three manifolds from physics, and to be able to compute them in some way. So let me remind you kind of at first a story which you are, many of you are probably familiar with. So consider Jones polynomial of a knot in a C. So we have a polynomial invariant of a knot, which is a polynomial, it's a variable Q, it's integer coefficients. And so yeah, so there is a way, of course, to combinatorially to define this invariant. By Witten proposed some sort of a more geometric interpretation of these coefficients, which in part explains why they are integers. So the interpretation of as a certain count of Kapustin-Witten, of solutions of Kapustin-Witten equations. So since Kapustin-Witten equations are in the title of my talk, so let me actually review what are they. So these are four-dimensional equations on the following fields. So we have A, which is a, so suppose it on a four manifold X. So we have A, which is a SU2 connection one form. So you choose a SU2 principal bundle over X, and you pick some connection, and phi will be a joint valued one form, and T will be a parameter which is a real number or infinity. And then we have the following system. Oh, I see. Yeah, thanks. So I should probably use this too. So we can consider the following system of equations where F is a field strength, is a curvature of my connection one form. dA is a covariant differential, and here plus mean takes we take self-dual part of this two form, and second equation is similar. We take anti-self-dual part, And we also add the following equation on phi. And what's important for our story is that if our form manifold is of the form y times r, these solutions to be known as gradient flow equations with respect to Chern-Simons functional. Well, to be precise, is with respect to the following functional. So it's a real part of exponent of ei theta times Chern-Simons functional of this blackboard bold A, which I explain in a moment. And I also tell you what is theta. So first, theta is related to this parameter t in the following way. So t is a tangent of theta over 2. And so A, blackboard bold A, is a combination of my SU2 connection and one from phi. So together they combine into SL to C connection one form. And Chern-Simons functional is the following integral over 3 manifold y okay. And then, so Witten's interpretation is that this AN, the account number of solutions of these Kapustin-Witten equations on a S3 times R plus, where we put a certain boundary condition, non-pole boundary condition at the origin of R plus. And we also, so we have consider a knot in this S3 at the origin, where we put also some singular boundary condition along the knot. And we count these solutions with fixed instanton number n. And also kind of from this point of view, one can also propose an interpretation. So these coefficients are known to be categorified by what is called Havana homology. And this picture, this categorification has interpretation as floor type homology associated to certain 5-dimensional Heidis-Witten equations, where we introduce an extra R direction. Questions? And so now, in principle, one can consider this story for homology.
Do you actually consider the actual solution spaces? That's the
No, this is yeah, I didn't write about categorification. I only said it in words. So here NN is just a number. Is a number. It's just yeah. You count these solutions with plus minus signs. Yeah. So categorification would be, so you introduce. So the for categorification, the solutions will form a complex, and then you form a differential on this complex by studying 5-dimensional equations on a 3 times R plus times R. Where at this other R you impose asymptotic conditions that these 5D Heidis-Witten fields the approach to solutions of these Kapustin-Witten equations. Yes. Yeah. So. Well, in Witten's paper in the late 80s, so he wrote the Jones polynomial as a path integral in the Chern-Simons to give T. But yeah, and this was, of course, was done well before Kapustin-Witten. But kind of one disadvantage of the story, so this gives you a kind of geometric interpretation of Jones polynomial. So you don't kind of use the particular kind of combinatorial description in terms of node diagram. But what was lacking is a kind of it was not for this because it was not obvious that these coefficients should be integers. So this was kind of lacking, and some motivation of this of the later work by Witten is to interpret this AN as in terms of a certain four-dimensional theory. But of course, interpretation of this physics interpretation of Jones polynomial in terms of Chern-Simons function theory, quantum field theory was, of course, yeah.
That equality is not a definition. The thing on the left-hand side equals an a priori unrelated thing on the right-hand side. Have some solution, some other unrelated thing related to some way.
Yeah, this is not a that is not a definition. This is an observation. Yes, I didn't write the definition. Yeah, that is not the definition.
Okay.
Yes. And yeah, one kind of hard part about this conjecture is extremely hard to count these solutions. I mean, by definition, like start with the system of equation and analyze it. Okay, and so from this picture, you can expect that there will be analog of this story. Well, you can write it on any manifold. It's a four manifold. Yeah, you don't need like spin structure.
Is there any format on which one?
I think on some like maybe three sphere, yeah, three sphere times R. I think people understand. Yes. Well, some people tell me they understand it on any spherical manifold times R, but they just didn't write it about it because it's boring. It's boring. Yes, yes. Yeah, and exactly. Well, I'm not, I can tell you in private. Oh yeah, this is going to be on YouTube, so I should be. So this seminar is not. So it's not. This seminar is not so informal. So yeah, so we can. Yeah, so we can kind of try to extend it to a general three manifold. Y. So consider Y times R plus, and consider like put again. So this non-pole boundary gauge has generalization for any three manifold. And here, so for S3, we have to put a asymptotic condition where there's a unique condition asymptotic, which gives me kind of finite energy solution. So you just this connection A should approach the unique flat connection, which is a trivial one on S3. But here now we have some choices of what flat connection we can approach at infinity. And
the non-pole is a sensitive where you place the non-pole.
Because the boundary condition, yes, it involves the knot. Yes, yeah, you don't involve. You don't. Yeah, here I don't. Well, I could put a knot, but I don't put a knot. It already becomes non-trivial without a knot.
In previous case, as R goes as a go to infinity.
Yeah, where you have a canonical choice, you just approach the connection approach is a trivial one. Yes. Because yeah, when you require, but here well, there is you should approach a flat connection to have some sort of finite energy solution, and but you have multiple choices of flat connections for general schema.
So when you have this SU2, you have a trivial SU2 bundle on manifold.
Well, for here for any three manifold SU2 bundle is trivial. also SL to C. Yeah, yeah. And in principle, you can do something like this. You can try to do something like this, and yeah, you can consider kind of corresponding Q series. And yeah, in physics, people, I mean, have been. This is some yeah, have been trying to do this. So in particular, this was kind of one of the first places it was analyzed is in the paper by Gukov, Pei, myself, and Wafa. No, it's well, physics gives you can consider definition for a class manifold. Some combinatorial definition for class. So, and again, the conjecture that these coefficients there they count Kapustin-Witten here. Well, this is known for certain surgeries on links which are closed closures of homogeneous. Well, I mean, yeah, as a combinatorial definition. Well, I'm saying the proposal for these guys has been made for many. The conjecture has not been checked. The conjecture has been checked only like for yeah, for very simple cases like 3-3. But the proposal, yeah, the proposal, yeah, was made. Yeah, if you wish, this gives a task to people to like differential geometers to solve these equations. So physicists, we make a conjecture. Like for mirror symmetry, people, the physicists first gave a proposal. Yes. But in my so.
But the text that was made related to things like the Jones polynomial and its cousins, right? Not to the game theory.
Yeah, this well, this kind of these guys can be understood as a sort of they're closely related to double variety invariant, where it's defined for like case root of units. So there's some sort of analytic continuation. You do analytic continuation of this, and but first of all, this is not part. It's not going to be focus of my talk. But let me just say it in word. So there's actually last week there was a announcement. Yeah. So we have, for example, explicit formula for these Plum manifolds. Yeah, you can consider as a definition. Yeah, that formula you consider as a definition, and then the conjecture that the radial limits to roots of unity give you double variety invariant. This was a conjecture which, well, at least there's a claim that it was proved in the last week paper appears which claims the proof this conjecture. Well, they're also a kind of combinatorial. You can say it as a definition for kind of more general surgeries, but there it has not been checked that it's actually invariant of 3 manifolds. So it's invariant on the Kirby moves. But for Plum's, it was checked that it's invariant on the Kirby moves. So then this is invariant of this class of 3 manifolds. And yeah, and the conjecture that this counts Kapustin-Witten equations, yeah, it has been checked maybe only for 3-sphere or something.
This conjecture is not equivalent to saying that Kapustin-Witten equation solution counts satisfy something.
It could be, yes, but I mean, first you have to define, yeah, for not you can consider well, but you also have to study then Kapustin-Witten for like not complements, which is it's also not an easy task. So we actually want to consider a simpler version. So well, we not want we can consider. My point is that you can consider a simpler version. So we just consider y times r, and so we put now a pair of flat connections. At infinities. And so we want to study something, some sort of generating series labeled by this pair of flat connection. And so they will be of the following form, where this is counts solutions again with these boundary conditions, and again with instanton number b and n. And so what I want to say is that I want to make again some sort of proposal, some indirect way to calculate these coefficients, or some proposal is what should this number should be for some large, relatively large class of three manifolds. This is a and they here T the solutions exist for only particular value. For given alpha beta, the solutions exist for only particular value of T. This parameter, this solution exists for only a special value of T. So if you fix this alpha betas, then in N, this value this T is fixed. Well, I mean, we consider this is a relation when you reduce on this four manifold being y times r, right? You want to study steepest descent flow when you introduce this phase. If you just write down explicitly this gradient flows, you get that.
Okay, so when T goes to 0, T goes to something special to that?
No. Well, I don't know. Well, it's some. Well, it's like this exponent is something like real or imaginary special values. But this is not. I wouldn't say this is something super special.
Not with that T0 and then something special.
Well,
yeah, nothing is special about T. It's I think what Manny said that nothing looks particularly.
You can divide by something, so you will only have some sort of cosine and sines. Yeah, you basically you could rewrite this in some ways that it will be tame. Yes.
No, but still, one of those terms or the other vanishes.
Yeah, just once it's like if T goes to 0, then you like this part you generally consider like if yeah, if T is 0, then the first equation becomes this, and the second equation becomes this. If T is 0. Yes. Yeah. But well, I don't know. But from the point of view of flow, well, no, yeah, well, this has some special direction in the real, there is some this real direction has some preference. Yes.
This was the question.
Yes.
What was the meaning of the special direction? That was the question.
Well, one question, yeah. So we will see actually this Chern-Simons function has, the real direction is special because, when you consider, the space of connections on the three manifold, so Chern-Simons, like if you consider the space of connections model gauge transformations, so Chern-Simons functional is not uniquely is multiple valued, and the so if you go around some non-trivial cycles, it shifts by integer. So in this way, well, I'm just saying that there is one preferred direction in this in the values of Chern-Simons function. What I'm saying is these Chern-Simons can shift by some integer, which is a real number. That's why there is preferred direction. In this way, this is I see that there is some preference. I don't other directions doesn't. Okay, this was the motivation part. So second part, let me try to briefly review the kind of relation between counting of gradient flows and Stokes phenomena in a finite dimensional case. So consider the case of the following integral, where we consider integration of a half-dimensional contour. Cn. So this S can be understood as some function, the holomorphic function from Cn to C. And so let me, for this review part, let me assume that S is Morse. S is Morse. And in particular, all critical points are isolated. But actually, for Chern-Simons, this is not going to be. If we then replace S with Chern-Simons function, this is not going to be true. But I mean, and one will have to make some adjustments. But let us not worry about that for the moment. So we have a finite set of critical points. So which I will label by alphas. And to these critical points, we can associate what is called Lefschetz symbols. Which is defined as a union of gradient flows from alpha, from this from Z alpha, so it flows in Cn with respect to real part of K times S. And then we can consider, so this, so we have some sort of critical point Z alpha, and has critical value, corresponding critical value, let's say psi alpha. So the Lefschetz symbol looks something like this. That's why it's called a symbol, and it projects to a ray starting at this critical value psi alpha. And so yeah, the slip is the gradient flow. So they go something like this, and we take the union. And then we can consider kind of, so in this, here we take a particular, we can take this particular contour of integration, which is given by this Lefschetz symbol. And then I can consider asymptotic expansion of this when K goes to infinity, and we'll have the following form. Some coefficients. Okay. And then we can consider the Borel transform of this. So in general, this is just a formal power series in 1 over K, not convergent. And then consider Borel transform. Which is a function, will be a function of Xi, which is naturally the variable which lives in this C to which we project. So the kind of the plane of our values of our function S. And we define them as a kind of as a series which obtained from this series by well, Borel transform. So it's a series in psi minus psi alpha. So you do some sort of some power shifts, and you divide. What is important? You divide by something which grows factorially with this n, and in particular, we introduce this gamma function. And then this I alpha in particular can be recovered from this by b alpha of psi as just integral of psi b alpha of psi exponent minus k psi, just a one-dimensional integral over this ray where our Lefschetz symbol got projected. So kind of we can say this b alpha, you integrate everything. So at each point you integrate over this. You kind of like you split this integration over the Lefschetz symbol, the integral over kind of phi bar of each point, and then the integral over this way. So in particular, you can understand this b alpha psi, some integral of this kind of volume, just as a kind of volume form over kind of half-dimensional compact cycle in this hypersurface psi equals s z, which, and this is cycle vanishing, which vanishes at psi equals psi alpha. Questions? Yeah, this is so far just finding like complex analysis of multiple variables. Yeah. Okay.
Let me just ask you if so suppose I had some function which was not this function that you wrote down, and it didn't come from this. Suppose I had some function on this bottom plane. It's like C.
Yes.
I have some function on the C plane. And this function on the C plane, I could ask for asymptotic expansion in some direction. But I would be allowed to do that. Yes.
Sorry, say it again.
You have a mystery function on this.
Yes. Okay.
Then I take some all of it, and I do take some array, and do asymptotic expansion. That's the thing I was allowed to. I suppose I have some asymptotic. And I'm trying to begin your story.
Yes. Okay.
So I do that. Then Morel transform is some formula I'm allowed to apply with asymptotic transform.
Yes. So yeah.
So is what you're saying that if my mystery function came in the way that you said, that this kind of push forward,
Yeah.
then the meaning of the Morel transform is the integral over the fiber.
Yes. Yes.
In other words, whenever I see someone write down, whenever I see someone write down this Morel transform, I should imagine.
Well,
they have some function came from somewhere else, and then they write this Morel transform. They're somehow imagining that.
Well, I mean, again, you can. This is only makes sense if it came from sort of path integral. Yes.
If I didn't know where it came from, and when they write this formula,
yes.
it's like saying there's some fantasy n-dimensional space, which I write some fantasy s, and yeah, that makes sense. But related to that, I have a question. What is the source of capital N? If I just began with some fantasy, so if I just began with some function like C.
So yeah, the capital N. Well,
I understand in your story you began with capital N. If I just
yes.
began with some function like C function, then when I do Morel transform, like this capital N is an input, right? It's a choice I make.
Yeah, the thing is that here you can kind of imagine that you change it, introduce some power of k originally here, and then you can actually define this, and this would so this will this will kind of change actually this B alpha, and it will start with a different kind of n. So it will change this B alpha, but what it's not going to change, it's not going to change its singularity structure. If you renormalize it by some overall power of k. You can principle what I'm saying. Yeah, this is subtle thing which I didn't want to discuss, but you can, if you renormalize this integral by some power of k, this will change. Of course, this will change B, but it's not going to change the singularity structure of B. Well, because I mean, you might not know what with which prefactor you started with. What was the prefactor in this integral?
That's the like the value of x that it's different.
No, sorry, no.
Isn't there something like
Sorry. Yeah, there is this, but this is not what I meant. Yes, thank you. There is indeed this. Yes, thank you. But what I meant, you can kind of rescale this by some factor here, and this will this rescaling it changes this B, but it doesn't change the singularity structure. But of course, like in Chern-Simons theory, it's supposed to be n is supposed to be infinite, but you don't. Of course, you don't start with infinite. You start with some point. You start with finite number. Yeah, well, this is a subtle point. This is actually this is discussed in our paper with Marinho and Google. But this is a technical thing which one can do. But this is like 1 hour to explain. I don't want to go to this. I can tell you. Yeah, these prefactors are important, and one can deal with them. But yes, well, this may. I'll tell about this now, essentially. So the point, kind of one main point is this B alpha has singularities at psi equals. So it can have singularities at other critical values with monodromies of the form. Where these are integer numbers. So they can. So in particular, it can happen if I kind of consider expansion of psi near psi beta, it has also some logarithmic dependence, and then it will have a monodromy. And the monodromy gives you this B corresponding to another critical point with some integer coefficients. And here the point is that this M alpha beta can be interpreted as kind of the usual Picard-Lefschetz theory tells us that these numbers can be interpreted as a number of gradient flows from alpha to beta. Maybe. Yeah. And the log counts as like a singular solution. Yeah, I guess you can write this kind of integral for like different Lefschetz symbols. Yeah, in some cases you can, I'm not sure. Okay, you can write as the different solutions of some. Yes.
So let's say gradient flow you have two symmetric.
Yes. It's no, well, no, this no, it shouldn't. Yes, its count should. My understanding it shouldn't. Yes. Yes, this is some sort of robust quantity. Yes, but this is not completely trivial. because this again, so yeah, so this has from this point of view, this has purely topological interpretation. It's just some sort of monodromy of half-dimensional cycle in your figuration. And but here indeed you have to choose a metric.
But is the statement that the d alpha coming from this feature, or like for any world transform any function in some time, or those the same?
Well, this is supposed to happen from Borel transforms of asymptotic expansion coming from some integrals of this form. Integrals where you have exponent of something times k.
Suppose I have some I alpha, which I can write down, but I don't know what
In general, I would know. I think this is a special. If you take a random thing, it's not going to have this nice singularity structure.
So you don't know any clear I'm saying. Suppose I alpha is a function of some kind of analytic class of some kind, then you apply Borel transform, then this is not true.
I'm not aware of this statement. I think there are more general class of resurgent functions which have this type of behavior, but then there's this coefficients are not integers.
No, wait. I mean, like, for example, I understand that.
This part is it's just a review of usual.
You could ask the question, like characterize all functions which arise.
I don't know the answer to this question.
But you could imagine that question with some answer and open the analytic properties of the function.
Yeah, but I know there's some. There's this some. You just start some reciprocal expansion and consider this resurgence machinery, and then you get this non-integer. This Stokes coefficient can be non-integers in general. And there you even there they assume some sort of I forgot this terminology of how this this asymptotic some there's some name for this class of this asymptotic X series for which you can apply this resurgence machinery. There are some statements, but I don't think it's a most general. It's a complete answer. Okay, now we kind of want this naively kind of see what this kind of how can we use this for Chern-Simons theory. We consider so we introduce analytic continuation of Chern-Simons theory on some three-manifold Y. So we can kind of naively consider an integral over in the half-dimensional contour gamma this is kind of naive from a mathematical point of view. This is a naive expression. So the integral, okay, there are some technicalities going on, which is kind of important actually. So you consider not the most usual space of connections, modulo Gauss transformation. What you consider is the following. So you consider a space of SL to C connections on Y, but you quotient it with respect to based Gauss transformations connected to identical Gauss transformation. And based means that you fix so Gauss transformation is described by a function from your three-manifold to this group. So you fix the value of this function at you pick a point at your three-manifold and fix this value of this function to be 1. And the relation between the more usual space is that if you consider quotient over Z, which Z is a group of large Gauss transformations, and you do extra quotient with respect to SU2, which is a Gauss transformation at a single point, so you get a more usual space of SL to C connections divided by gauge. And this, so why this? Do we need this first? So we want to get rid of kind of large gauge transformations because we want to K to be operate a complex number, and we don't want to only want to quotient with respect to base gauge transformation because we want this space to be kind of smooth because this action SU2 action is not free action. Anyway, this is some technical points which you can ignore.
How can this type of point possibly be relevant to getting compliance in a dilemma?
Well, this is for how morally you should think about it. Yes. Is it, forget. Yeah, you can ignore this if you don't like this. So, okay, in what follows, we assume that Y is a rational homology sphere. So the first homology is fine. And so the main point is the following. So although this path integral is not mathematically well defined, its perturbative expansion is. And to define, and you said before, to define this B, we actually need its input. We can consider its input as the just perturbative expansion. In particular, we can consider perturbative expansion around trivial flat connection. You need to have this well-defined perturbative expansion. Usually, at least in the most classical approach, at least.
The consequence of that is that the trivial flat connection
is isolated. Yes.
The derived sense. So it has no tangent vectors.
I'm not sure. I don't know. I cannot vouch for this. Maybe you can. You can still define direct without passing. You can define directly analog of these I integrals over Lefschetz symbols, where you consider Lefschetz symbol corresponding to trivial flat connection. Depends what is your contour. What is the contour here? I didn't tell you. I mean, you can in analytic continued theory, you can take any contour. If you want to reproduce double Rayleigh invariant, you take a very special contour. But then any contour you can decompose into linear combination of Lefschetz symbols. Here I'm talking about considering possibility just a contour which is a Lefschetz symbol corresponding to a trivial flat connection.
And which is the thing which corresponds to double Rayleigh?
It's a special contour explained in the Witten's paper how you take this contour. It's not unique. It's not unique because you only want to reproduce double Rayleigh K is integral. So there can be different contours for which the limit when K is integral gives the same result.
And this somehow has the effect of summing the expansions.
Yeah, then there's a question how this Witten double Rayleigh contour you can decompose into Lefschetz symbols. And then you make some statements. So for example, one statement that all SU2 flat connections, they enter with coefficient 1. Like Lefschetz symbols corresponding to SU2 flat connections, they enter with coefficients 1. But they're with what coefficients enter Lefschetz symbols corresponding to some SL2C connections, which are not SU2 connections, it's not always known. But of course, in the asymptotic expansions, they suppress, they exponentially suppress those.
But this is how like it's not almost mathematically well defined. Take this special Witten contour and expand it to symbols, and I get well-defined numbers. Is a question.
Sorry, I mean, can you say it again?
The question is, assume this thing.
Yes.
That is mathematically well-defined, some number associated to each or the function of K or whatever associated to each flat connection. So this Witten contour sums up the connections
No, I don't think it's no.
I'm not saying it can compute it. I'm saying it's not defined.
No, I don't think so. No. No. Yeah, you have to calculate intersections between this WRT contour with F symbols. I don't know. Is this some middle dimensional contour? I don't know. I don't.
You're saying that it's not defined.
I think already this WRT contour is not mathematically well defined.
Okay, already. But it's only a set, right?
Anyway, I'm not interested here. I'm not interested in WRT. I'm not. Well, I'm interested in WRT, but this is not going to be important.
Sorry, but it's not special contour. It's just that it's not classical. We're just rewriting it, right?
Not quite, because of this difference. Because if you take as a just naive SU2 contour, it's not going to be closed contour in this A tilde space. So you have to make a funny prescription how you close it, because this is not. It's not going to be because you didn't divide by all gauge transformations. So this contour, like naive, here you can take like just subspace of SU2 connections, but if you lift it to A tilde, it's not going to be closed. It will have a boundary, so you have to extend it. And there is not. It's not a unique. It's not a unique way to do this.
But the nature of this finding this coefficients of these symbols, I'm supposed to compute the intersection numbers.
Yes. Yes.
Which are half-dimensional interdimensional space. That's the task.
Yes, you have to compute the intersection. Yes.
Your critical manifold for this Kapustin, it's like a manifold.
Not always. I think.
So is that
sometimes it is.
Yeah, is that supposed to? Well, you should take some of that boundary in your critical manifold.
Yeah, how to define symbols in this general case? It's more. No, I told you that it's going to be relaxed. Here, it's not. The kind of only trivial is isolated actually. No, this is only trivial. This gives you that the trivial is isolated.
You could assume they were all isolated.
No, it never happens. If in this lifted, it never happens. But for example, if you consider irreducible flight connection, like if it's isolated here, there it will lead to like copy of SL2C. So the minimum, like for reducible flight connection, the minimum you can have is like copy of SL2C. It's actually important here. For example, if you have like trivial and here you can have like trivial isolated irreducible flight connection, which look kind of the same. They're both points here, but if you lift there, they become, one of them becomes point and the other becomes non-trivial manifold. This is important. Okay, so you can define. So this is these coefficients here can be mathematically well defined. So they are related to what is called Atsuki invariant or finite type invariance. This is a definition for me.
No,
if you want.
Definition should be
because I don't have it here. We don't know the right hand side is not. So this is going to be definition.
No, but I thought the right hand side is supposed to be write down some pattern diagrams.
Well, for finite type invariance, this is in Kontsevich, for example, right? He considers, yeah, this like they consider universal finite type invariance, which is this kind of linear combination of these guys, which physically comes from perturbative expansion. Is this what your question? It's Kontsevich. Also, Dorban down. I think it's some papers in the 90s.
I know they wrote something, but I'll look again.
Okay. But practically, you can calculate them as Atsuki. Okay, and And then from this, we can define, again, B0 of psi as just a Borel transform. So you divide the coefficients by some gamma. Okay, now let me introduce some notation. So we'll make this clear. Okay, so we have this. I kind of already mentioned this partly inverse. So we have by alpha, we will denote connected components of the usual moduli space of flat connections, which is a critical set in this A, the space of SL2C connections in SL2C connections on the three manifold. And by alpha tilde, we'll denote a corresponding lift. This will be in the connected components of the critical set of Chern-Simons functional in considering this larger space A tilde. And again, the relation between these two is a quotient Z and SL2C. And so for fundamental groups, they're just related by like free action of Z. So for each component here, there is a Z worth of components here. And oh, sorry, did I write? Yes, yes, sorry, SL2. Well, anyway, they are homotopy equal. And so, for example, for this type of thing, we have a well-defined Chern-Simons functional, well-defined as an element of C mod Z, right? But here we have well-defined Chern-Simons functional as a complex number. And again, the relation between these two is kind of mod 1. So in particular, in principle, for a single connected component here, we actually have a tower Z kind of tower of connected components of critical sets in this larger space.
This is not the original assignment where the typical just point number. It's the London dual. That's why we talk about a different content.
No, I think it's.
Okay, so the infinite number, we call that K. Is K going to become more complex?
Here, K is complex, yes. So it's already.
In other words, the expansion is in e to the 2 pi I K times an integer.
Sorry, what do you mean? I only expand in one case so far.
So no, eventually, when you get a Q series.
Eventually, well, there my Q is formal power series. Q is, but in principle, these are series in 2 pi I K. Yes, you can say, yes. So in principle, it's actually expansion in Q tilde. Yes. But the way I introduce Q, it will be actually just a formal parameter. But yeah, in principle, there is this. Yes, you're right. Forget about this. I have not yet come to this point. I will explain when the time is.
You wrote down some time ago, and if you restrict that to some particular contour, then you get the 1998 paper.
But
in a non-trivial way, that's not an object.
There will be some series in this Q, which is actually probably should be called Q tilde. But yeah, they are naturally will be series in this 2 pi I, while the Jones polynomial are naturally kind of, well, polynomials in 2 pi I divided by Q. What I will have actually, yeah, the series with integer coefficients in Q tilde, which I call, yeah, my Q will be actually Lagrange double Q. I have not yet come to this part, to this Q. No, but this is related, yeah, to relate this directly this to, for example, double T invariant, you don't need to replace K with minus K, 1 or K. It's just the point of this parameter Q.
In 1988, you write either 2 pi I K or either 2 pi I over K.
K, like this, K. And there it was important that K is integral.
K is actually over K is actual Jones polynomial.
Yes. And Q, yeah, there Q was. Yeah, I mean, yes.
The Chern-Simons theory
But-
related to Kapustin-Witten theory is not the Chern-Simons theory. In general, that of the line with two.
Yes, yeah, the Kapustin-Witten, which will be Lagrange double. Yes.
Okay, but everything so far is still happening in the same Chern-Simons theory as this Witten Christian.
Well, I don't know what it's. So original Chern-Simons theory was defined just for integral K. There is not making no sense to consider 1 over K. Perturbative, well, okay, sure.
I mean, the sense in which this specializes between us.
Well, again, there is some special contour, which gives exactly that expression, gives you double RT at Q equals 2 pi I over K. Yeah, well, it's because we already discussed part of this before, I think. Yes, it hasn't appeared yet. But I think, yeah, maybe, yeah, to be kind of proper, I should call my Q as Q tilde, but I was too lazy to use tilde.
But you never wrote down this.
Yes, but yeah, that's why I wanted you. That's why I wanted you to ignore this.
When you were writing a Q in this, what Mina is saying, when you were writing a Q in this Jones
Yes.
or whatever.
Yes, that Q naturally has meaning like this. But the way I introduce Q actually will be just as a formal parameter. So it doesn't. I don't care about I don't care about the relation with Q with K. So yeah, so okay, and we define this B0 in this way, and then we can make the following conjecture. So this B0 can be so first it can be analytically continued to the cover of C with these critical values of Chern-Simons functional removed. And it has a monodromies. Part of the conjecture is it converges in a finite non-zero radius. This is yeah, I didn't write it. Yeah, it converges in finite disk.
I mean, sometimes when Sergey gives talks, he tells me that like it's known that.
No.
Maybe
Well, yeah, I don't think it's well. In principle, I guess you can maybe prove it by there's some sort of if you have some sort of bounds on these coefficients, finite up environments, maybe. But I don't think it's. I don't think it's. As part of this, yeah, it's converges in finite disk. If analysis of the form. So it's a monomy at xi equals xi alpha. So well, Chern-Simons.
Yeah,
Yes, this is what I. Yeah, this is the value of Chern-Simons function with some representative. You choose some representative in the connected component and you evaluate the Chern-Simons function. Doesn't matter which representative you choose by definition. Where these guys actually after a shift, they only depend on alpha, not on alpha tilde. And these coefficients are integers. Well, you can have either like if everything goes here, well, like the simplest situation, you only have like double branch cuts, like order 2 branch cuts and logarithmic cuts. Yeah, logarithmic points and kind of quadratic roots. Yes, yes. Yeah. And moreover, the guys which appear in the monodromy, they themselves have monodromies at other critical values. Again, this in principle, they only depend on this projection. So if you assume that this conjecture is true, so we can define, yeah, so we can define this E alpha beta. So our visuals, so yeah, sorry, I'm going to use the Q here, but maybe it would be more appropriate to use Q tilde. But anyway, here I use Q as a formal parameter. So we define this E alpha beta as, so you do a sum over all lifts of fixed flat connection beta of M alpha tilde beta tilde, and you weight it with a difference of Chern-Simons function of this beta tilde minus Chern-Simons function of alpha tilde. And this will give me some october of power shift, some formal power series in Q and Q inverse. And what I want to say is that up to an overall integer, one can determine one particular I0 alpha just from the knowledge of our B0 or equivalently I0. And then if I0 alpha is non-zero, then we can also determine I alpha beta by kind of repeating this procedure. If this sum of these coefficients is non-zero, then we can find these guys and determine their monodromies.
How is that supposed to separate out which alpha? How do you use that formula to determine the alpha?
So here I want to determine these coefficients, right?
I agree. Suppose you knew those coefficients. Suppose you knew they were all one.
So which coefficients? This? Well, you see, this is a you consider you consider monodromy.
At any point, only one such thing. There's not a sum or else.
No, it's there is no sum here. There's no sum here. Well, that's yeah. The point here, yes. If we think that the thing, if you assume that things work as an finite dimensional case, then this M should count flows with respect to Chern-Simons functional between this critical, yeah, between the connected components.
When do you expect that those would only be or like I wouldn't expect between any two critical flows.
It's not like more flows, big things.
Yes,
All the critical points, in a certain sense, are the same way. They're all going to make zero. But if you look in a one-parameter family, then like as you rotate this kind of direction, in isolated moments, you'll still have this relationship between critical points.
Yeah, you only have flows for particular values of this angle, which you consider the flow.
So this is a difference between
Yes, yes.
So you're saying H lower one Y is like the finite thing, although a portion H1 element.
Yes, yes.
And that connection on this Y, you still have like continuous.
Well, the point here is for trivial connection will be isolated.
But
For non-trivial, it can still have families. Yes. Actually, this is a point which I want to make a remark. So critical points are not isolated. And in particular, this implies that you don't necessarily have this symmetry, which you would have from the usual Picard-Lefschetz.
Are there some toy examples where you like take vector space, finite-dimensional vector space, finite-dimensional group acting?
Yes, yes.
Take some function.
Yes, yeah, it's in Witten's paper. Yes, there's a nice finite dimensional example where like you have a like one point. Yeah, one is isolated critical point, the other is a orbit of some U1 action. Yes, it's a nice, very nice example, and you can see that it's already there. Analytic continuation of Chern-Simons theory. And there's also a bit more complicated example in our paper, Gukov, Marini, or myself in the appendix. There are some finite, some nice finite dimensional examples. So in particular, so what you if connected components, so how do you actually, so why, from the point of view counting flows, this might be not obvious. So why does this happen? Because if you look at this kind of picture, schematic picture, you would say, okay, alpha and beta enters in a symmetric way. Why there is a asymmetry here? But the point, which is actually made again in this paper by Witten, is that, well, assume a simple case when if connected components are of the form M, connecting components of critical points are of the form that the total space is a cotangent bundle of some compact let's say, even assume that this is a manifold. then what you want is this M alpha beta tilde to be count flows kind of from the base of one connected component to a fiber at some point of another. So if you kind of schematic picture, if you have two kind of connected components, which looks like this total spaces for canonical bundle, so we count flows from the base to the fiber. So in general, we have to pick some sort of compact cycle in one connected components and some sort of dual non-compact cycle in the other connected components.
So the connected component, are they do I think of them as an homogeneous or symplectic? So the local system on surface to equal surface are like symplectic.
Yeah, that's the answer. I think we'll be happy with it.
So it's not actually thinking that's an
It's an Andy space that is critical of this. No. It's like the intersection of two graphs. That's kind of language.
So the bottom line here, if you kind of know asymptotic expansion, so you can kind of construct this, but it's a Borel transform, and then you can analyze its analytic properties to deduce this kind of the monodromy coefficients. And the point is that this kind of for fixed kind of connecting component of flat connection, the singularities actually in this Borel plane psi, they organize in some sort of towers. So for each of these kind of representatives in the tower, we have particular monodromy, and you can combine these all monodromy coefficients in a kind of Q series. And they can, the singularity, they in a single tower, they just come shifted by an integer, which corresponds to kind of shift of Chern-Simons function by an integer.
You're asking why is this cotangent by the path? You're asking why.
Well, this is roughly comes, I think, from the fact, or in my understanding, this is kind of natural because this is a T star of SU2. So one is the orbit of SU2, the other is a cotangent. In kind of a simple situation, one is the orbit of SU2 and the other is a cotangent bundle with the orbit.
It's also probably it has something to do with the fact that everything is that.
This is not, I don't think it's, this is not true in general.
Yes. In this case, I'm just saying that we haven't discussed the kind of hypergeneous measures. Thanks so much for this.
Yeah, you can. Yeah, see, there is simply there is symplectic form on this on the space. Yes.
Not just symplectic form,
I think so. Yeah. Okay. So and now, so I come to the final fourth part. So how much time can I? Okay. See, so before it was basically a review of known stuff, and then I want to kind of apply this machinery to a particular class of three manifolds.
So Kapustin-Witten equations, the four-dimensional variance, right? It's not
Yes.
from the singular setup to begin with, but they do.
Yes. Yeah. They. Well, again, the just like twisted version of n equals 4.
First, we take a break.